take like a linear space, like grad level class. Or class in, no, take functional analysis. Yeah, yeah, they do. They're offering it right now. It's not called functional analysis. It's called linear operators. You should take it. I was gonna take it, but I decided like it would be like too much work.
You should start us.
Well, I mean,
Hey, Micah, are you ready?
yeah, I'm ready. It's already. Yep, it's all good. Well, we're not streaming, but it's on a timer. It'll start in 1 minute.
Yeah, this is fun. Alright, let's start. So I think until last time we saw a whole bunch of algorithmic techniques, and today I want to start with a quick review of these. Okay, and I want to move on to the next topic, which is NP complete. So let's do a quick review first. Okay, so first, before we start, a couple of announcements. So the homework one is due on Thursday. Hopefully all of you got started. And so what's the general feel? Could most of you solve most of the problem? Okay, so hopefully... No. Okay. Okay, so the answer to that will always be no, but I guess if you can solve 2 or 3 of them, it's probably nice. Yeah, but I mean they're all meant so that I mean 2 or 3 of them should be easy, and a couple more should be difficult but doable. Maybe one is not doable. Okay, so that's my goal. Okay, so but yeah, we'll see. So the other announcement I have, which is probably more important, is this mailing list. So this is something I was hoping to do earlier, but I didn't know if there was a Utah infrastructure for this. So if you want to contact me and the TAs all at once with something that you don't want to post in a discussion, then you can send email to this address. So maybe there will be a link to this also on the course webpage. But yeah, just wanted to announce this. And yeah, all right. So so I wanted to start with a quick recap. So the last few weeks we did a whole bunch of things, right? So let's do a quick recap, right? So the goal was to give you a sense of the basic paradigms when it comes to algorithm design, right? So we started off with divide and conquer, okay? And there, in some sense, the interesting things were how you analyze the running times. Okay, so we said we saw how you go through an algorithm, set up a recurrence relation for its running time, okay, and we saw how you analyze such recursive running time. Okay, so that was the first thing we saw, this by drawing the tree, etc. Then we saw one of the examples we saw there, which was non-trivial, was this finding a median in linear time. And we also saw proofs by induction. Okay, so we said that for most algorithms which you do by divide and conquer, you try to prove this by induction. Okay, so we saw the proof technique, which is induction. Okay, then we moved on to dynamic programming, which we said is very much like recursion but done well. Okay, so we said that you try to avoid recomputations, try to make things faster by just kind of keeping track of solutions so far. And this turned out to help. We saw a whole bunch of examples for this. Maybe not too many, but we saw this example of a longest increasing subsequence. Then we also saw this coin change problem, which is related to this, and so on. Okay. So that is dynamic programming. And afterwards we went on to looking at greedy algorithms. So these are algorithms where you build a solution by doing the best possible at every step. Then we said that these kind of algorithms don't usually work, but sometimes, but usually they are useful to know. Okay, they are the first things you should try. And so we saw a bunch of examples. So the first one was coin change, where we saw that sometimes greedy algorithm works, sometimes it doesn't. Okay, and then we saw this greedy matching, and we showed that you always get some, you don't always get the optimal solution, but you don't do too badly. So this is what we did for matching. And last class we also saw this thing of this, what's called interval scheduling technically. So you have a bunch of classes and you want to take as many of them as possible. We said that simple greedy rule of taking the one that has the least finishing time does well. And so with greedy algorithms, the non-trivial thing is always how you analyze them. Okay, so how you prove that they return the right answer. Okay, so and there's no general way, but often what works is you try to look at what the algorithm did, and you try to see what an optimal solution could do. Okay, and you try to compare these two. Okay, and then you show that you're not doing too badly compared to the optimal. So this is how we analyzed greedy algorithm. And finally, we saw this example of local search, where it's kind of like greedy, but in some sense, it's not a one-shot thing. Okay, so we said that you start with some solution, which you construct by whatever means you want, and then you keep updating. Okay, so you try to see if you can change the solution a little bit and maybe increase the objective value. Okay, or improve the objective value. So this was what is called local search, and the examples we saw are optimizing some function over a grid, and we also saw this parallel machine scheduling. Okay, so this problem we might come back to this when we are doing some NP hardness type reductions. Okay, so these are in some sense the essential techniques you should all know about coming up with algorithms, and these are many of these. I guess you would have seen in your undergrad classes on algorithms. Okay, so this is meant to be more of a recap. Okay, so starting in about a week or so, we are going to move on. Okay, so what you can see from next time, you can describe it like this, right? So we're going to try to apply our methods. Okay, so this is kind of what will happen. Okay, so we'll try to see. Okay, so we learned all the basics. Now, when you apply, you'll stumble, but then we'll try to figure out how you pick up. Okay, so that's the goal. So, questions about any topics that you thought maybe it's good to spend more time on, stuff like that. So we could. Yeah, so maybe if you have such questions, do email me, and right before the fall break, maybe we could do one class of just recapping things that maybe people want to see again. Okay, so alright, so let's move on. So now, today I want to talk about So far we've been stressing this question. You consider some problem and you say, what's the fastest algorithm I can get, right? And if you remember, we were almost never satisfied. We kept asking, can you do better? Is there a better way of solving this, and so on. Okay. Now, one natural question you can ask is, are there limits to how quickly you can solve problems? Okay. And if so, how do you prove such limits? Okay. So that's kind of the question we want to understand in this next couple of classes. And it turns out this is very difficult, because so what you are saying is, you want to say that no algorithm, no matter how clever, can actually run faster than this, or something like this, right? So, and these kind of statements are very hard to make. Okay. So the first simple question we'll consider is how quickly we can sort n numbers. So we've seen merge sort, we've seen a bunch of sorting algorithms. And they have some running time, and the question is, can you do better than that? Okay, and so this is one question we'll see today. So this is one of the few examples where we can actually show that some algorithm we know is actually optimal, okay, under some assumptions. And we'll also generally study this question of, are there natural problems for which there's no really efficient algorithm. Okay, so I'll mention what that means in a bit. So this is a question that we want to understand. All right. So let's so let's start with this sorting question. Okay, so let's say you have n numbers, okay, and you want to sort them. And one thing we saw was merge sort. So what was the running time here? Okay. So merge sort took n log n time. And so note that we could ask, can we do O of n, right? Because reading the whole array takes only n time. So maybe you can do it in time that's just O of n. So this is a natural question. And what do you guys think? So can you do it in just linear time? Sorry? That's sometimes, right? Yeah. So, yeah, I'll come to that in a bit. Okay. So what we want to show today is that if you have an algorithm that only works by comparisons, okay, so what the algorithm is allowed to do is you have this array A1, A0, A1 up to An minus 1. And the algorithm is only allowed to ask you questions like, is AI less than AJ or something like this. Okay. So you only allow comparison queries. And so what we're going to show today is that any algorithm that only does comparisons must take at least n log n steps. So in some sense, merge sort is optimal if you only allow comparisons. Okay. So what do I mean by that? I'll formally state what that means in a bit. But this is roughly the theorem that we are going to prove. So in some sense, you can't do better than n log n for sorting. So before we go on, I just want to recap this homework problem. Okay, where so firstly, by sorting by comparisons basically means you are only allowed to ask questions of this kind. Okay, so this is what I wrote before. Yeah.
Shouldn't it be best case, or I'm trying to figure out why it says in the worst case?
Okay.
Yeah.
So in the worst case, in the sense that so you want to be able to sort every possible array of length n. So that's why we say the worst case. So basically, what this means is, you want an algorithm that is always correct, right? So any such algorithm must take time at least n log n. So that's what this means. Okay, so any algorithm that works on any input of size n, of length n. Yeah, that's a good question. So worst case usually means that. So there could be an algorithm, if you get like a half sorted array, maybe it could do much better, right? So what you're saying is it should correctly sort every array, and it should only use comparisons. Okay, so as I said, comparison. So such an algorithm, essentially, the only way it has access to these numbers is by asking questions like, is A of I less than or equal to A of G? So that's the only way it accesses this array. And we saw that otherwise you could do things that are smarter, right? So like suppose I tell you that I give you n numbers between 1 and 100n, okay? And I ask you to sort them. So can you, so I guess all of you would have done this. So can we sort in O of n? So I tell you that all the numbers lie between 1 and 100n. Okay? So the range is quite limited. And Yeah, any hints? How would we go about solving this?
Basically, you just need to count the number of occurrences of each element.
Right. So one simple thing could be, you say you have a different array that's of size 100n. Okay. And you can tell if and now you can go through the original array. Okay, so this is the original array A, and you can say, oh, okay, so I know this lies between. I know that entry lies between 1 and 100n. Okay, so these are numbers from 1 to up to 100n. And I can say, oh, okay, so this actually is here, and okay, I say that this number appeared once, this number maybe 2 appeared twice, and so on. And knowing this, you can just reconstruct the original array, right, in sorted order. But note that what we are doing here is not comparisons, right, because we are actually looking at the values of what is there in this element. Okay? So we are looking at the original array and we are doing something numerical with the numbers. Okay? And what we want to consider here is algorithms that are not allowed to do this. Okay? So what we want to say is the algorithm only has access to the data by using comparisons. Okay? So you could say this is an artificial model, but almost every algorithm we know for sorting actually falls into this. Okay? So these kind of special cases are a little bit different, where you will have some guarantees about these elements. But any general purpose sorting algorithm will just work by comparison. Okay, so most reasonable things like merge sort, quick sort, all these things work by just comparison. Okay, so that's the kind of algorithm that we want to study, and we want to show that any algorithm that just compares must take at least n log n steps. Okay. So how would we go about proving such a statement, right? So it's tough to do this, but first let's try to think, right? So how could any such algorithm look like? We said that it compares some elements, and then it could do some operations. It could like move one element to the other. It could create some new array, do some calculations, and so on. But the only way it accesses the original array is via these comparisons. So is this model clear? So do you all get a sense of what kind of algorithms we are talking about? So maybe I can take some questions, because this is a slightly subtle notion. Okay, so we are talking about algorithms that essentially just compare, and then they are allowed to do any other operations. But the only way you get access to these numbers, to the array itself, is via comparisons. Okay. So that's the kind of algorithms we are looking at. Okay, so good. So what it does is a few comparisons, and it does some manipulations and so on. Okay, and so the main idea behind proving this kind of a statement, but note that we don't know what comparisons it's doing or what outputs it's getting and so on. Okay, and we want to show that if this algorithm works correctly for any input, then it must make at least n log n comparisons. Okay, so that's what we want to prove. Okay, so let's see how you go about doing this. And the idea is actually it's very clever. So what you say is, okay, suppose I fix some numbers. Okay. So let's fix some numbers b1 through bn, which are all strictly in increasing order. Okay. And let's say there is some algorithm A that takes some bunch of n numbers and sorts them. Now what we are saying is, suppose I give this algorithm, okay, so the algorithm I'll write it as ALG, just so that my two A's won't be confusing. So the algorithm is called ALG, okay, and it gets as input this array A, and I'm going to give it as input these numbers b, but in some jumbled order. Okay, so the numbers, so b's are these numbers that are nicely in sorted order, and I'll permute them, okay, and produce this array A. Okay, so it's a reordering of these b's, and this A is input to alpha. Okay, is input to the alpha. Now, so how many such inputs are there? Firstly, so every input is just a reordering of these n numbers.
N factorial.
Yeah, so there are exactly n factorial possible inputs. Okay. And somehow the key trick to this analysis is to say, let's look at two different inputs, okay, and let's see how the execution of this algorithm differs when we consider these two different inputs. Okay. So note that if you take two different inputs, the algorithm doesn't know these BIs, right? So it should figure out that these two are both permutations of the same B's. Okay. So, okay. So this is the idea that you want to consider. So okay, so let's consider this algorithm ALG, and let's assume that it performs some k comparisons. Okay. All right. So what I want to claim is that if 2 to the k is less than n factorial, then there exist two different permutations that have the same answers. Okay, so let me see what that means. Let me tell you what that means. So let's look more carefully at this algorithm ALG. Okay. So what is it doing? It's doing k comparisons. Okay. So initially it will ask you some question like, is ai less than aj for some I and j? Then it will do some manipulations. Okay, maybe it has some memory, it works with its memory and so on. Then it will ask you some other comparison. Okay. And so on, it does some k comparisons, and then it outputs the sorted array. Okay. So it outputs a permutation of these a's. Okay. So now, so what I want to say is, suppose I start with two different permutations of this b. Okay. And so before going there, actually, so note that the answer to every comparison is either yes or no, right? In some sense. So it asks, is ai less than or equal to aj? Right? So that's the kind of question that the algorithm is asking you. Okay, so one way to think about it, if it helps you, is imagine you are interacting with the computer. Okay, you are interacting with this algorithm. The algorithm asks you questions like, is a of I less than a of j? Okay? Less than or equal to a of j, and you say yes or no. Okay? So what this means is, if it asks you k queries, there are only 2 to the k possible answers you could give. Okay? Because every answer is just yes or no. And the algorithm goes and does something once you give it an answer, but that doesn't matter, right? So over the course of this algorithm, the total number of answers you could give is only 2 to the k. Okay? So is that point clear? Okay. So now, suppose you start with two different permutations. Okay? So I start with pi 1 and I start with pi 2. So note that if all the answers you gave are roughly the same, are exactly the same, okay? So it asks me, so pi 1 basically corresponds to one input a, and pi 2 corresponds to some other input a prime. Okay? And it asks me, okay, is ai less than aj? And imagine running this algorithm with these two inputs. Okay? And suppose I get exactly the same answers. then note that the algorithm should do the same thing on these two arrays, right? So that will be what we'll use. Okay? But first, let's prove this claim. Okay? So if 2 to the k is smaller than n factorial, then we are saying that that there exist two different permutations for which all the answers will be exactly the same. Okay? And the reason for this is, so what's the reason for this?
Pigeonhole principle.
Yeah, it's exactly pigeonhole principle, right? Because if you ask k questions, there are only 2 to the k answers. And if you have n factorial different permutations, and n factorial is bigger than 2 to the k, then 2 of the permutations must have the same set of answers. Okay? So this is actually quite simple. And then we are saying, okay, so let's start with these two permutations. Okay, so we know there exist two permutations for which you have the same set of answers. Okay. We are saying that if the algorithm only does k comparisons, then it gets the same answers for both these permutations. So its behavior on both these permutations is exactly the same. Okay. So if the same answers to queries, to all k queries, its behavior on the two inputs is exactly the same. So is this point clear? Because the algorithm interacts with the array just by doing these comparison queries. Okay, so this is where we are using this fact. We are saying that so if it gets all answers, I mean if two permutations produce the same answers, then its behavior is exactly the same. And yeah, so and this is it, right? So if it does the same thing with two different inputs, then it has to be wrong on one of them. Okay, because let's say it correctly sorts this A. Okay, then it will sort A prime also in the same way that it sorted A. Okay, but then both these answers cannot be correct because A and A prime are both two different sets of numbers. I mean, two sets of n different numbers, and they are in different orders. Okay. So if it produces the same sorting for both of them, then at least one has to be wrong. Okay. So is this argument clear? So yeah, so maybe we can just go back and think about this, but it's actually very simple. So what we are doing is you take a bunch of numbers, you permute them in different ways. We are imagining running these two different inputs on the algorithm, okay. And we are saying that if the answers to all these queries are the same for these two permutations, then the algorithm must sort them in the same way. Okay, sort them in exactly the same way. Okay, which means that if it produces some A of pi 1, so let's say let me call it. Let's say let's for simplicity assume that the algorithm outputs A of 0, A of 1, and so on. Then it must produce the exact same output for this A prime also, because for all it knows A is A prime, right? And so it will sort both of these in the same way, and both of these can't be correct. Yeah.
But the output is a sorted array, right? So if the algorithm is correct,
yeah,
then both the outputs have to be the same. So if the algorithm is wrong.
Yeah. So that's another way of saying this. So this automatically implies that if 2 to the k is less than n factorial, then the algorithm is necessarily wrong.
So for one of them, you get an unsorted array.
Yes.
As the output.
Yes. Because yeah. So this is another way of saying this. That if it makes only k comparisons, and 2 to the k is less than n factorial, then it means that the algorithm has to be wrong on one of the arrays. Okay? So it can't be correct. Okay? So yeah, so implies algorithm is incorrect. Okay. So what we've proved is that for any correct algorithm, you must have 2 to the k to be bigger than or equal to n factorial. Right? So this is just the converse of this. So here we showed that if 2 to the k is less than n factorial, then the algorithm is necessarily incorrect. So it means that for any correct algorithm, you must have 2 to the k to be bigger than or equal to n factorial. Okay. And what this means is that k is bigger than or equal to log to the base 2 of n factorial. And what is log to the base 2 of n factorial? Yeah, so one way to see this is, it's at least, so n factorial is this, so it's log of n times n minus 1 times n minus 2 times so on, times 1, and okay, so what is this asymptotically? Actually, maybe we saw this in the first homework, or did we? But one way to easily bound this is, so it turns out that that n factorial is roughly n to the n divided by e to the n. Okay, so you can use that to conclude that this is roughly n log n minus some O of n. Okay, so log e to the base 2 times n. Okay, so this is, for those of you who know, this is one way of doing this. But for those who don't, note that you can always say that this is bigger than or equal to n by 2 to the n by 2. Why is that? So I'm saying that this product n times n minus 1 times n minus 2 times so on is bigger than n by 2 to the n by 2. This you will be able to come up with. So intuitive. So So what can you say about the second half of these numbers?
They are all greater than n by 2.
Yeah, exactly.
N by 2 of them are greater than n.
Right, so you have at least n by 2 numbers, each of which is bigger than or equal to n by 2, right? And these are all bigger than 1. Okay, so the 1 through n by 2, you just bound them by 1, and these are all at least n by 2. Okay, so this is trivially bigger than or equal to n by 2 to the n by 2. And so what that means is that this log term is bigger than or equal to log to the base 2 of n by 2 to the n by 2, and this is at least n by 2 times log of n over 2. Log of n over 2 is just log n minus 1, right? So it's I can write this as this, and this also gives you this bound of some constant times n log n. So in this case, the constant is half. Okay. So this easy argument gives you n by 2 times log n, and if you do a more careful thing, you get n log n. Yeah.
Sorry, in the bottom right hand corner, that scribble, is that just n by 2 times log n minus 1?
Yeah, so yeah, I wrote initially log of n over 2, and log of n by 2 is basically log n minus log 2. Log 2 is 1, so yeah. Okay, so this is it, right? So what this shows is that the number of comparisons must be at least this number. Okay? So it shows that if k is smaller than this number, then you have that there exist two different permutations that give the same answers, so the algorithm is necessarily incorrect. So this is a clean lower bound, so it shows that in some sense what merge sort is doing is optimal. Okay, and so this is also one of the few examples of a lower bound that matches an upper bound. Okay, so usually it's hard to come by. These kind of results are hard to come by. Note that here also you had to make assumptions. Like you had to assume that the only way the algorithm accesses this array is via these comparisons. Okay? So, any questions about this? So I guess some of you seemed a little bit lost during this proof. It's probably because I did it in a slightly mixed up order. But if you just go back and think about this, and first try proving this claim that if you get, if you have only k queries and 2 to the k is less than n factorial, then there are two permutations for which you get the same answers. So that's just pigeonhole principle. Once you assume that, you say that, okay, let's start off with two different permutations for which you get the same answers, then the algorithm should behave the same way on both these inputs, and which means that it's wrong on one of these. Okay, so the algorithm is not always correct. So an always correct algorithm has to have k at least log of n factorial, and that is at least n log. So that's the very simple answer. Okay, so this is for sorting. So let's so you could ask, okay, so what is true for other problems, right? So there are more interesting problems. Sorting is just one basic example. Okay. So let's consider another problem which kind of is very important in computer science, and this is what is called Boolean satisfiability. Okay, so how many of you have seen the satisfiability problem before? Good, many of you have. So let me just go through it anyway. Okay, so this is George Boole. Forgot the name, but write the name. So Boolean algebra is something that Boolean logic or Boolean algebra is something that we see often in computer science, right? So it is so you have variables xi, and each xi is supposed to take values true or false. Okay. And so it is also called Boolean logic, right? So this. So you have variables that take values that are true or false, and then you have these operators, right? So you can say xi or xj. This is the symbol for or, and you can say xi and xj. And xk or something like this, and this is and. And there's also a symbol for not, which is you can say not xi. This is so this is basically the negation. If xi is true, not xi is false, and so forth, and the other way around. Okay. So I hope all of you have seen Boolean algebra in some way or the other. Okay, and if not, it's very simple. Okay, so it's basic logic. So so what is a Boolean formula? So a Boolean formula is basically an expression of this kind. So you have some variables x1 through xn that are all Boolean variables. Okay, that means they are true or false. And a Boolean formula is an expression that is made up of and, ors and nots of these variables. So it could be something like x1 or x2 or x3 and x3 or not x4 or x5 and something else, or a more complicated thing, right? So you could even have an or here. So just assume you have, so we know how to evaluate this. So that's a Boolean formula. So any questions? So does anyone have a question about what Boolean formulas are? Because I'm assuming all of you have seen this before. So Boolean formula is just an expression that is formed by and, ors, and nots of these variables. Okay, so that's the formal definition. So now, once you have a formula, you can ask, okay, so do there exist values, true false values for these variables xi's, such that the whole formula becomes true? Okay, so let's take an example. Okay, so let me take an example. Let's take a simple formula. Okay, so x1 or x2 or not x3. So this is a very simple formula. Let's start with this one. Suppose I ask you, is there a setting for the variables x1, x2 and x3 so that this is satisfied? So that this evaluates to true. Trivially, because you can set, let's say, x1 equals true, and no matter how you set the other guys, this formula will evaluate to true. Okay, because I set this to be true. But suppose I ask you, okay, so this and something like not x1 or x2 or not x3. Is there a setting for x's such that this is true? This is also true, right? Because now you can set x2. Now this one is not very helpful because I want both these to be satisfiable, but now I can use x2, right? Okay, so that's fine. And so you could also have, okay, so what happens if I set not x2 over here? If I had not x2 and then maybe I had x3. Is this still satisfiable? Yes, right? Because you can always try to make one of them satisfiable. You can always make one of x1 and x2 be the right thing. Okay, so you can set this to true, this to false, and then this would become false, but this would be true, or something like that. So there's always so these kind of things exist. But on the other hand, you can write down formulas that are not satisfiable, right? So you can, like a trivial example of this could be x1 and not x1. So this is clearly not satisfiable, okay? Because you can't make both of these true. Okay, so this is the satisfiability problem, and so you're given some formula in n variables, and you want to figure out do there exist x1 through xn such that the formula evaluates to true. So any questions about this problem? Okay, so now that we've seen this, so how would you solve this problem? Yeah, you can, that's one way. So you can say, okay, I want to find if there exists some x1 through xn. So I'll try all possible things, right? So you could say, okay, so I will set x1 equals true, x2 equals true, so on. I start with the all true assignment, and then you can evaluate the formula efficiently. Okay, so you can evaluate the formula, and then you can see if that evaluates to true. Okay, so if not, you try the next assignment where maybe you set this to false, set everybody else to true, and so on. So what's the running time of such a procedure?
2 to the k.
It's 2 to the number of variables, right? Which is, I said that there are x1 through xn, so there are 2 to the n. This takes time 2 to the n times the time to evaluate. So given an assignment, what's the time to evaluate? So suppose I tell you one setting of x1 through xn, and I ask you to see, okay, does the formula evaluate to true or false? So what's the time to evaluate? It depends on the size of the formula, clearly. I guess that's why you guys are all puzzled. So So it's basically, it is proportional to essentially, it is some polynomial in the size of the formula. Okay. So let's call this formula phi. So I will say that this is some poly in phi. We don't, for now, let's not care what exactly that polynomial is. Okay, so it's, you can probably make it linear, right, as you would imagine. Okay, so, all right, so you have this as the running time, and the basic question is, so this is one of the most fundamental questions in computer science, which is there an algorithm for this problem, for this Boolean satisfiability problem, which runs in time polynomial in n? And this is also called the P versus NP question. And so essentially what we are asking is, for satisfiability questions like this, can you avoid exhaustive search? Okay, so exhaustive search takes time, which is like 2 to the n. And what we are really asking is there a very smart way of finding an assignment which avoids this kind of exhaustive search? So suppose I give you some formula that is, okay, so implicitly what is there here is I give you a formula that is size of phi, let's think of it as poly in n. Then can you have a procedure that overall runs in just time polynomial in n? Okay. So polynomial in n basically just means it's n to the c for some constant. C. Okay, and so this is the, so this is one of the most fundamental questions. So we'll see in a bit why this is so significant. Okay, so what is so significant about this satisfiability problem? Okay, so we'll see that in a bit. But any questions about the problem? So you have a formula, and you have, this is in some n variables, and you want to figure out if you can find an assignment that makes the formula evaluate to true. And so we want to do this in time poly n. And the surprising thing is, we don't know the answer to this. So that's another reason why this is very notorious. Just that there's no proof that you can, people believe that this cannot be done, but we don't know of a proof that this cannot be done. Okay, so this is one of the most important open problems. So firstly, let's try to answer this question. Okay, so why is this very significant? This seems like a specialized problem, right? So why care about the satisfiability? And the reason is that it has kind of a philosophical point of view. Okay, so it goes back to this theme of what is called solving versus verifying. So what we are saying is, suppose I give you this mathematical statement. So does anyone recognize this statement? Yeah, so this is one very simple version of Fermat's last theorem. It says that if you look in the integers, then there is no non-trivial solution. Okay. Non-trivial just means one of them is 0. Okay. So one of them is 0, then there are obviously some solutions. But so we want to say that this equation has no non-trivial integer solution. So this is a mathematical statement, right? And this has been proved. So this version of it actually has a fairly simple proof. Okay, so you can go through it, and you spend a couple of minutes, you will understand what the proof is, right? So I don't intend you to literally go through this, But yes, so we can go through this step by step, and then we can verify that the proof is correct. Right? But now the question is, suppose I ask you to come up with the proof. Okay? Now, I guess all of you will agree that coming up with a proof is significantly harder than verifying that it's correct. Right? So I guess all of you would see it, like you have a tough homework, you see the solutions, you're like, oh okay, this is how you do it. But you can verify that it's correct, but coming up with it is tricky. And somehow the P versus NP problem captures exactly this. Okay? So let's see why. Okay? So what is going on when you are verifying a solution? Right? So what we are essentially doing is, you can think of the solution as some, it's a write-up, right? So it has some formulas, it's writing, I mean you have some mathematical symbols and they're all arranged in some particular order. Okay, so that's what a proof is. And so verification is simple, right? So you first check if step 2 follows from step 1 and whatever axioms you've assumed about the integers. Okay. So I'm still considering this for my example. Okay, so it's a statement about integers, so there are some axioms we know about integers. And you say, okay, so check if step 2 follows from step 1 and these axioms. And then you check if step 3 follows from these 2 steps and the axioms and so on. Okay. So each of these checking statements is actually, each of these check statements is actually some form of you could state it as some form of satisfiability problem. Okay, so what you are saying is, so what do we do in each step? We just see if it mathematically follows from this step 1, step 2. Right? So you can think of it as some formula phi which consists of step 3, step 2, step 1 and the axioms. And this formula evaluates to true if and only if step 3 follows from step 1, 2 and the axiom. Okay? So if you think about it a little bit, you can convince yourself that you can always write things like this. Okay? So any proof you can kind of write it as some kind of a Boolean formula, and this formula is true only if this follows from this. And then what we are saying is, so this is for step 3, and then you have some, let's call this phi 3, and then there's phi 4, which takes 4 steps and so on. But overall, let's say I have a proof of length n, so that is a proof has n steps. N steps. Then there are n such phis. Each of them is like polynomial sized. Okay. So overall, this is just a poly-sized formula. Okay. So let's not go into the formal details of this, but I guess intuitively you can convince yourself of this, right? That any proof, every step of verification you can write it down as as a formula, check if everything is consistent, and then you have n steps. So you have n of these. You want all of them to be true, so you put an and of all of them. You want all of them to hold. Okay. And so this is so what I said is a heuristic argument, but this can actually be made formal. Okay, so I won't go into this. So this is what's called the Cook-Levin theorem. So this is one of the fundamental theorems in computer science. So what it says is that you can phrase any verification problem as a satisfiability problem. Okay, so this is again an informal statement, but it's something of this kind. Okay, so you have any verification problem and you can write it as a satisfiability problem. Okay, so as a Boolean satisfiability. So this kind of hints at why satisfiability is important. right? Because what this is saying is, so if I have, so suppose Boolean SAT can be solved in polynomial time. So then what this previous argument is saying is that, so in some sense the solving time for this is polynomial in the checking time. Okay, so this is the verifying time. So is this point clear? So if Boolean SAT can be solved in polynomial time, so that means you can find a satisfying assignment. So what does it mean that Boolean SAT can be solved? You can find an assignment to phi, find an assignment x1 through xn such that phi of x1 through xn is true, right? So we are saying that you can quickly find an assignment, okay? And so if you can do that quickly, then it's like saying that solving this problem takes time that is not much bigger than just verifying that it's correct, okay? So, and this is something very surprising, right? So this is not what you would expect for mathematical statements. Somehow we believe that there is this creative process that goes into, in some sense, solving the problem. Checking is more of a mechanical process. Okay? And so if SAT can be solved efficiently, so that means that solving is not much harder than verifying. Okay? And that's why it has these philosophical implications, that in some sense, there's no, you can in some sense automate this creative process. Okay? So that's, it would be great for doing homework, but would be bad for various other things. So that's what the P versus NP actually says. Okay, so this is how you should understand it. Okay, so questions about this? So this is one thing that all of you should, in some sense, realize. And so this is the implication of P being equal to NP. Okay, so it's saying that solving a problem is as easy, roughly speaking, as verifying that the solution is correct. And that is something that we believe inherently is not true. Okay? So, but surprisingly, we don't have a proof for this fact. Okay? So it's just everyone believes it to be true, but we don't know the proof for this fact. Okay. So let's move. Okay, so before I've been calling this the P versus NP problem, but I've stated it as just satisfiability, right? So let me go into this definition. Okay, so what are these P and NP? Okay. So guesses? So what is P? Yeah, so let's go with P, right? So what is P? Yeah, so one thing is both of these are set of problems. Okay, so that's the first thing. So both of these refer to what are called complexity classes, but it's essentially a set of problems. Okay, so this is an informal definition. Okay, so P is a class of problems that can be solved in polynomial time. So what does it mean solved and so on? We have to be more careful about this, but this is an informal definition. Okay, so we all, I guess we all have a natural model for a computer and we know what solved in polynomial time means. Okay, so that's what I'm assuming now. Okay. So what is NP? Yeah, so one answer which none of you should give is that it's not polynomial. Okay, so NP is it's actually, it has nothing negative about it. Okay, so it's actually a positive statement. So what it says is the set of problems. So I'll write a definition, and maybe some of you will know what it is, some of you might not. So it's the class of problems that can be solved efficiently, solved in poly time, on a non-deterministic Turing machine. Okay, so I haven't defined what this is, but think of this like a very special computer, okay, which can guess all the right answers. So I won't define what it is because this is not very important for us, I mean for this course. But so have most of you seen this notion of a non-deterministic Turing machine? Okay, so I guess Turing machine is, everyone understands, it's just like a regular computer, okay, but a non-deterministic one, they don't exist, or we don't think they exist. But what is an alternate way of defining this class is just by saying the class of problems that can be verified in polynomial time, okay? Whose solution can be verified in poly time. Okay? So this is exactly what we were saying. Like the satisfiability problem belongs to this class NP. Okay? Because this is a problem for which, as we said, if I am given a solution, you can tell in polynomial time, this poly in phi time, whether that solution is valid or not. Okay? But producing the solution is actually a difficult thing. Okay? So that is the class of NP problem, where you know that there exists a solution that is verifiable in polynomial. One thing to note is that every problem in P is also in NP. Okay. Because basically if it's easy to solve, then you can then verify it and so on. Okay. So if you have solved it correctly, it means that you have in some sense verified it. Okay. So we know that P is a subset of NP, but we don't know if it's a strict subset or not. So we don't know that there exist problems in NP that are not in P. So that's so, and literally the $1 million question is P not equal? So you know that one is contained in the other, but we don't know if it's a strict. Okay, so these are things that you should know, and the important thing to note is that so there is this notion of non-deterministic Turing machines, and NP is just the class of problems that can be solved in polynomial time on such machines. Okay, and that informally just means problems whose solution can be verified in poly time. So good. So hopefully this clear. Okay. So what we were saying is okay. So that this is a big question, right? So we were saying that okay. So we believe that SAT is not in polynomial time, and we want to understand that we said that there are all these philosophical implications. Like this means that, for instance, that it's something good. So if SAT is not in if SAT cannot be solved efficiently, so one question you could ask is, what does it tell me, right? Because we just said that if SAT can be solved efficiently, then all proofs can be automated, the world becomes a much simpler place. But what if it cannot be? Okay, so what does it tell us? So it could give us lower bounds. Okay, so what it could do is, it would imply that a lot of other problems that we care about, cannot be solved efficiently either. Okay, so that's the thing that we'll study next time. So there is this notion of reductions. So, and the idea behind the reduction is that you prove mathematically that if SAT cannot be solved efficiently, then neither can my problem. Okay. So note that, as I said, proving that a problem cannot be solved in polynomial time is something that we don't know how to do. Okay, so that is this big P versus NP question. Okay, and so the next best thing to say is, I have this problem, I'm not able to solve it, but but you could say that if I could solve it, then I could also solve SAT. Okay, so that's the notion of reductions. Okay, so you say that SAT is something that we all believe cannot be solved. Okay, so it's in some sense appealing to faith. Okay, so you're saying that we believe SAT cannot be solved efficiently. You're saying now I have this whatever problem, right? So we'll see a bunch of examples next time. And if I could solve this problem, I could also solve SAT. But I believe that is not possible. So that's so that's the idea of reduction. Okay, so we'll see examples next class. Okay, so and I want to end with I just want to end with this cartoon. Okay, so this is from this book of Gary and Johnson. Okay, so what if your boss gives you a problem and says, okay, come up with a solution for this. Okay, come up with an efficient algorithm, right? And you don't want him to fire you because clearly, and so this is one way of thinking about reductions between NP-complete problems. Okay, so you say that I can't solve this problem, but it's not my fault. Okay, so neither can all these famous people because we believe SAT cannot be solved. So we'll see concrete examples of reductions next time, but this is the general idea. Okay, so I wanted to stop here because I don't want to get into reductions.